One of the most fundamental concepts in all of chemistry is the concept of the mole. And it's appropriate that we're talking about that very first here in Unit 1 of AP Chemistry. The SI unit of substance is the mole. And when we use that term, we're talking about a very large number of objects. That number, as you might read, is 600 to sextillion. Of course, it's not practical to write that number out most of the time, so we usually use scientific notation. And we say it's about 6.02 or 6.022 times 10 to the 23rd items or objects.
You will pilot it. You will pilot it. You will pilot. You you will pilot. You will pilot. You will. You will. You will pilot. You you will. Will pilot. You will pilot it. Will pilot. You will pilot. You will pilot. Will pilot. Will pilot. You will pilot. You will pilot it. You will pilot. You will pilot. You will pilot. You will pilot it. You will. You will pilot it. You will. Will pilot it. Will you will. will pilot. Will
That's how many things there are in a mole. That's a very large number. Now, just to illustrate this, if we had that many grains of rice, and you all know that grains of rice are very, very small, that would be enough to fill all the land area in the whole world to a depth of 250 feet. That is a lot of rice. That's more rice than has been grown since the beginning of human history, as far as we know. If you had about that number of hockey pucks, that would have about the same mass as the moon. On the same scale, that many molecules of water, it's a very small amount. In fact, it's about 18 milliliters, or about 6/10 of an ounce of water. So by thinking about this, we can see how large this number is. By the way, this number 602 sextillion, 6.02 times 10 to the 23rd, we call this Avogadro's number. Sometimes because it is named after Amadeo Avogadro, the scientist who did some of the work that helped us to discover that number. This also helps us to see that Avogadro's number represents atoms, molecules that are exceedingly tiny. It is unimaginably small to think about how small atoms and molecules are. Very, very small objects. That's why we need such a big number to talk about them. Now, when we describe a mole, if we talk about 1 mole of carbon, that is specifically referring to Avogadro's number, 6.02 times 10 to the 23rd atoms of carbon. If we talk about a mole of water, well, water doesn't appear in atoms. Its unit is called a molecule. So that would be referring to Avogadro's number of molecules of water. If we say 1 mole of sodium chloride, well, the
pilot it. Huh? Will pilot it. Will pilot it. Will you will pilot. Will pilot it. You will pilot it.
the unit that we use for sodium chloride is not called a molecule. Since it's an ionic compound, we call it a formula unit. So that would be Avogadro's number of sodium chloride formula units. 1 mole of bromine, Br2, that would be that many molecules of
Piloted. Will piloted. 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 Will piloted.
bromine. If we have ions, we can talk about a mole of ions as well. That just means 6.02 times 10 to the 23rd sodium ions. We can use a mole to talk about pretty much anything. A mole of anything really just refers to 6.02 times 10 to the 23rd fundamental units of whatever that substance happens to be, whether it's an atom or a molecule or an ion or a formula unit, whatever it happens to be. A mole is just 602 sextillion of those objects. Now, we can work problems with this as well. Here's a nice example of that. Let's say we have 0.380 moles of carbon dioxide, and we want to figure out how many molecules of carbon dioxide we're dealing with. Well, we work this problem just like we have before in the introductory unit. We learned about dimensional analysis. And if we're converting from moles to molecules, well, you want to put moles on the bottom, because whatever unit you start with needs to go on the opposite side of the conversion factor. And then since we're converting to molecules, that's going to go on top. And we've just learned that 1 mole is the same as 6.02 times 10 to the 23rd molecules of pretty much any compound there. So we can cancel moles. And on our calculator, you're going to take 0.380 times Avogadro's number. And when you key that in, you get the answer 2.29 times 10 to the 23rd molecules of carbon dioxide.
Worry. Scott 1000 lasts 2 times longer.
And we can go in the other direction as well. If we have a question that says a sample of 1.02 times 10 to the 24th ions of calcium, 2+, is equivalent to how many moles? We work the problem pretty much the same way, except we write down what's given to us here. This time it's 1.02 times 10 to the 24th ions of calcium. And this time we're converting it to moles. So at the end we're going to have moles. And our conversion factor this time, ions will go on the bottom and moles will go on the top. And we know that 1 mole is equivalent to Avogadro's number of ions. So we can cancel ions. And this time we're going to divide. We take 1.02 times 10 to the 24th and divide that by 6.02 times 10 to the 23rd. And when you key that in, you should get an answer of about 1.69 moles of calcium. Now, just as a reminder, I'm trying to be consistent with my significant figures. My question in both of these examples actually had 3 significant figures. So my answer should have 3 significant figures as well. Try to be consistent with that. Now, another way to talk about a mole is with the mass. What is the mass of a mole? You know, it's honestly not very practical to counting atoms and molecules. No one's ever going to sit down and start counting atoms. Take a look at a table. Let's count, 1, 2, 3. It would be impossible, basically ridiculous to actually sit down and count atoms. The way that we count is by weighing or by finding the mass of a mole. The mass of 1 mole, if we look at any periodic table square, just look at the atomic mass right there and express that atomic mass in grams. And so as you can see down here, 1 mole of copper is going to have a mass of 63.456 grams, as we can see. And that works for pretty much any element. 1 mole is equal to its atomic mass expressed in grams. And if we have a compound, it works the same way, except you just have to add up its individual atomic masses. So if we have salt, sodium chloride, and you want to find out what's the mass of 1 mole of salt, well, you're just going to take the individual periodic table squares and add up the atomic masses. So sodium is about 22.99, and chlorine is about 35.45, so that gets us about 58.44 grams in 1 mole of sodium chloride. Just so you know, in this course, I will try to round these off to the nearest hundredths place. That's a good habit to get into. Don't round off too much. Try to get you enough significant figures in there so that it doesn't adversely affect your answer whenever you do calculations with this. So that's why I try to use 2 decimal places on these. Now, we call this the molar mass, as in the mass of 1 mole of a substance. So we'd say the molar mass of sodium chloride is 58.44 grams, or the molar mass of copper is about 63.55 grams, molar mass. Now, we can also use molar mass and talk about it in a very, very tiny